As in our previous class, we learned that a pre-stress concrete member undergoes direct stress as well as stress due to moment caused by the pre-stressing force, and apart from these stresses, stress generated from the self-weight of the member and imposed load working on it also is active. But to move further, first we need to know what is pre-stress and what is its principle. As first of all, what is pre-stressing? It is the process of induction of compressive stresses in the structure before it is put to its actual use is known as the pre-stressing. And these are some very common applications of pre-stressing in our daily life. Now, what is pre-stress concrete? As we simply call pre-compressed concrete, and it is a member of concrete in which internal stresses are introduced in a planned manner so that the stresses resulting from the superimposed loads are counteracted to a desired degree. And the position and magnitude of this pre-stress force can be chosen so as to suppress any tensile stresses that are expected under working load. But why do we pre-compress concrete? As we know, pre-stressing is the intentional creation of permanent stress in a structure or assembly for improving its behavior and strength under various service conditions. In case of ordinary concrete, consists of concrete and mild steel as basic components. The compressive stresses are borne by concrete, while tensile stresses are borne entirely by steel. The concrete only acts as a binding material, and it does not take part in resisting the external forces. But in case of the pre-stress concrete, compression is induced prior to loading in the zones where external loads would normally cause tensile stresses. And in case of long beams, the long beams, where the large shear forces exist, the beam sizes have to be large to limit the diagonal tensile stresses under certain limits. Pre-stress decrease diagonal tensile stresses. This has led to adopt modified I section and T section in which there is substantial reduction in wave area. And all these things can be achieved either by pre-tensioning or by post-tensioning. And we will know in a video how this pre-stress is done and how the pre-stressing concrete section is formed. I will upload a link along with this presentation so that, and you please go through this video and you can have this idea of the entire pre-stress process. Now we come to the applications. What is the applications? What are the applications? As you can see, the pre-stress can be used in this kind of buildings or structures, that is underground structures, towers, water storage, offshore structures, numerous types of bridge system including cable stayed and segmental bridges, nuclear reactor vessels. And these are some pictures of very commonly used pre-stress structure where pre-stress concrete is used. All for now.
Talk to any concrete professional and they'll tell you the #1 rule of concrete is this: it's pretty much guaranteed to crack. But not all cracking is considered equal, and there's a way to reinforce concrete to minimize its negative impacts. Hey, I'm Grady, and this is Practical Engineering. Today, we're talking about pre-stress concrete. This video is sponsored by Dashlane. Never forget a password again. More on that later. Despite its excellent qualities as a structural material, concrete has some weaknesses too. One that we've discussed in previous videos is that it has almost no strength against tension. Concrete can withstand a tremendous amount of compressive stress, but when you try to pull it apart, it gives up easily. Concrete's other weakness is that it's brittle. It doesn't have any give or stretch or ductility. Combine these two weaknesses and you get cracks. Concrete loves to crack. And if you're designing or building something made of concrete, understanding how much and where it's going to crack can be the difference between the success and failure of your structure. To understand how engineers design reinforced concrete structures, first we have to understand design criteria, or the goals of the structure. The obvious goal that we all understand is that it shouldn't fall down. When a car drives over a bridge and the bridge doesn't collapse, the structure is achieving its design criterion of ultimate strength. But in many cases in structural engineering, avoiding collapse actually isn't the limiting design criteria. The other important goal is to avoid deflection or movement under load. Most structural members deflect quite a bit before they actually fail, and this can be bad news. The first reason why is perception. People don't feel safe on a structure that flexes and bends. We want our bridges and buildings to feel sturdy and immovable. The other reason is that things attached to the structure, like plaster or glass, might break if it deflects too much. In the case of concrete, deflection has another impact: cracks. The reinforcement within concrete is usually made from steel, and steel is much more elastic than concrete. So in order to mobilize the strength of the steel, first it has to stretch out a little bit. But unlike steel, concrete is brittle. It doesn't stretch, it cracks. So that often means that concrete has to crack before the rebar can take up any of the tensile stress of the member. This demonstration is from a test in a previous video showing a conventionally reinforced concrete beam. Go back and check out that video if you haven't seen it yet. Notice how the beam is resisting the load on it even though it's cracked at the bottom. It's meeting design criteria number 1, it's holding the load, in this case 6 tons, without failing. But it's not meeting design criteria number 2, serviceability. It's deflecting too much, and the concrete is cracked. Those cracks not only look bad, but in an actual structure they could allow water and contaminants into contact with the reinforcement, eventually causing it to corrode, weaken, and even fail. One solution to this problem of deflection in concrete members is pre-stressing, or putting compressive stress into the structural member before it gets put into service. This is normally accomplished by tensioning the reinforcement within the concrete. This gives a member a compressive stress that will balance the tensile stress imposed in the member once it's put into service. A conventionally reinforced concrete member doesn't have any compression to start with, so it will deflect too much well before it's in any danger of not being strong enough to hold the load. So with conventional reinforcement, you don't even get to take full advantage of the structural strength of the member. When you pre-stress the reinforcement within concrete, you don't necessarily increase the strength, but you do reduce its deflection. This balances out the maximum load allowed under each of the structural design criteria, allowing you to take fuller advantage of the strength of each material. There are 2 main ways to pre-stress reinforcement within concrete, and of course I built a demo to show how this works. The first one is pre-tensioning, and yes, that's a little bit confusing. It's pre-stressed because the steel is stressed before the member's put into service, but pre-tensioned because the steel is stressed before the concrete cures. To make this work, I had to build a little frame to go around my concrete beam. This frame will hold the steel in tension while the concrete cures. I installed threaded rods through the mold and frame, and then tensioned these rods by tightening the nuts. I tried to use the pitch of the ringing to get them at around the same tension, and you can see how much my frame is flexing from the force in these steel rods. The other method for pre-stressing steel is post-tensioning. In post-tensioning, the steel is stressed after the concrete cures, but still before the member is put into service. In this beam, I cast in smooth plastic sleeves in the mold. The steel rod can slide easily within these sleeves. Once both molds were prepared, I filled them up with concrete. And I finally got a construction-grade concrete vibrator as well. This machine helps get all the air bubbles out of fresh concrete before it cures, a process called consolidation. After the concrete's had some time to cure, it's time to test the beams out. On the pre-tension beam, I can unscrew the nuts and take off this frame. Because the concrete hardened around the bolts, the steel rods are still under tension inside the beam. I put it under the hydraulic press for testing, and the results are easy to see. In a conventionally reinforced beam where the steel is simply cast into the concrete without any tension, cracks start forming at around 4 tons. In the pre-tension beam, the cracks didn't appear until double that force, at around 8 tons. The tension already in the steel is able to take up the force of the press without requiring the beam to flex. For the post-tension beam, I inserted the steel reinforcement after the concrete had cured. Then I tightened the bolts on the rods to pre-stress the steel. Under the hydraulic press, the results are nearly identical. The tension in the steel held the beam in compression for much longer than a conventionally reinforced member could. Of course, the cracks eventually appear, but it takes much more force before they do. That's because adding force to the beam isn't necessarily creating tension at the bottom, but simply reducing the compression that's already been introduced through the tension in the steel rods. It's important to point out that we didn't make these beams any stronger. Both the steel and concrete have the same strength they would without pre-stressing. But we did increase the serviceability of the member by reducing the amount of deflection under load. Of course, none of these examples actually failed because of the reinforcement, and that wasn't the point of this demo, but it's still fun to test everything to failure. Pre-stressed concrete is used in all kinds of structures, from bridges to buildings to silos and tanks. It's a great way to minimize cracking and take fuller advantage of the incredible strength of reinforced concrete. Thank you for watching, and let me know what you think. Thanks to Dashlane for sponsoring this video. I've been the victim of at least 10 major online data breaches in my life, including Facebook, LinkedIn, and Equifax. Obviously, all those passwords have been changed, but if I was reusing the same password for all my online accounts, any data breach could give people access to my bank accounts, health records, and everything in between. Dashlane simplifies online security and password management by seamlessly integrating into your browser and syncing between any kind of device automatically. And it's more than just a password manager. Dashlane warns you if stolen personal information is found in a data breach, can help you change passwords without going through a maze of web page settings, and has dark web monitoring and a VPN. I've been using Dashlane for a while now, and I really enjoy the peace of mind knowing my online accounts each have their own password that I don't have to try and remember on my own. Support this channel and visit dashlane.com/practicalengineering to sign up for free. Use promo code practicalengineering to get 10% off a 1-year premium subscription. Again, thank you for watching, and let me know what you think.
Now, our current slide is on advantages of prestress concrete. The first point is durability. Actually, durability is one of the most premium advantages that a prestress concrete structure has. As we know, this technique eliminates weakness of concrete in tension. Such members remain free from cracks. Hence, it can resist the effects of impact, shock, and reversal of stresses more efficiently than a normal RCC structure. Also, they provide reliable long-term performance in extremely harsh conditions that could destroy lesser materials. The next point is adaptability. The precast pre-stressed concrete products can be designed and manufactured for any application, ranging in size from short span bridges to some of the largest projects in the world. Also, it permits precast manufacturers to vastly expand the design variety possible using precast components. The next important advantage is fire resistance. As the structures are not easily damaged by fire and they have excellent fire resistance property, low maintenance costs, elegance, high corrosion resistance, etc. The next advantage is fast and easy construction. This is also an important advantage of prestress concrete. Why is it so? Because precast concrete components lend themselves to fast construction schedules. Precast manufacturing can proceed while the site preparation is underway. Precast units can be delivered to the job site and installed the moment they are needed to in any weather. Fast construction means earlier completion and the resulting is cost savings. It saves the cost of shuttering and sintering for large structures. The next important advantage is the aesthetics. Precast components can be delivered with a wide range of shapes and finishes, ranging from smooth, dense structural units to any number of architectural treatments. Strikingly rich and varied textures. Sorry, strikingly rich and varied surface textures and treatments can be achieved by exposing color sands, aggregates, cements, and coloring agents using sandblasting and chemical retarders. Stone, tile brick, and other materials can be cast into precast panels at the factory, enabling designers to achieve the expensive look of assembly. But there are some disadvantages also, which are that is the unit cost of high strain materials being used is higher as mostly high tensile steel is used. The cost of the high tensile steel is very high. So as here the high tensile steels are used, so the cost of the material is higher. Following, the extra initial cost is incurred due to use of pre-stressing equipment and its installation. The installation of such pre-stressing concrete structures is high. The extra labor and transportation cost for pre-stressing is also there. So, in case of the pre-stressed concrete, cost is an important issue, which is a big disadvantage. Thank you.